So we are going to start this new section, the Riemann-Stieltjes integral. This is an extension of the theory of Riemann integrals we have developed so far. And this theory is eventually going to give us the two fundamental theorems of calculus, with one of which we are already familiar. It's that one which we used in school calculus to calculate definite integrals. First you find the antiderivative, then upper limit minus lower limit, that thing. Okay, so let us start this. Now, this is similar to the theory of Riemann integration. Let's recall what we did in the very beginning of Riemann integration. There, we first of all, the very first thing we did is defining the length of a bounded interval. Say you have a bounded interval of real numbers and the interval is degenerate. Let us first recall the notion of length, the definition of length. Degenerate means the interval is either the empty set or consists of a single real number. These are the two cases which we express by saying that the interval is degenerate. In these cases, the length of the interval is was defined to be equal to 0. And the non-degenerate cases are these. I can be a closed interval or a half open interval of this type or a half open interval of this type or an open interval where a and b are two real numbers and a is less than b. In these cases, we defined the length of I to be simply b minus a. Now we are going to start this theory, this new theory, the extension, with a modification of this notion of length. Alpha length, we call it alpha length, where alpha is going to be a function. So let's see the definition. And we will also see how this new definition is a generalization of the ordinary notion of length. Let I be a bounded interval in R such that I is a subset of X where X itself is a subset of R. I is contained in some larger set X. Let alpha be a real valued function on X. Okay, so this is the setup. Then we define the alpha length of our interval I denoted by this symbol. Alpha, then I within square brackets, as follows. Here also we separate the degenerate and non-degenerate cases. If I is empty, this is not how it appears in the book, the author writes in words, but the meaning is same. If I is empty or I is this for some real number a, then the alpha length of I is defined to be equal to 0. So the alpha length of a degenerate interval and ordinary length of a degenerate interval same, 0, it's 0. So here the definition is just the old definition, nothing new. Now let I be of the form this or this or this or open interval a comma b, where a and b are real numbers and a is less than b. So now we are having the case where I is non-degenerate. Then the alpha length of I is defined to be equal to alpha of b minus alpha of a. Ordinary length is b minus a, alpha length is alpha of b minus alpha of a. Now I said that, I think I did not say this, but we will now notice that there is something slightly wrong with this definition. It doesn't seem anything is wrong at first, but let's see this case. Let us take a specific alpha, and that will show us that there is something wrong. Suppose I consider this function alpha of x is x square. Fine, we can consider the square function on this open interval. So the x we have in this definition now is the open interval 1, 2. Since the requirement is that our bounded interval I needs to just be a subset of x, so I can in fact take I to be this interval itself. So in this case I and x are the same. So what will be the alpha length of I? By definition it will be alpha of 2 minus alpha of 1. Well, you will say that there is no problem because it will be 2 square minus 1 square. 4 minus 1 is 3. However, you may fail to notice a very subtle thing here. Note that the function alpha has x as its domain. Now, in this case, of course, we know that the square function, the rule which tells you to square the input, that is actually defined on the entire real line. But that's not the case with every function. You may have a function alpha which is defined only here. But then what is the problem? The problem is that there is no alpha of 2 and there is no alpha of 1 because 1 and 2 are not points in the domain of alpha. That's the problem. So what should we change here so that this is also answered, this is also taken into account? A simple change that we can make here is this. We are going to require a little more. Instead of requiring that I be a subset of x, I now require that the closure of I be a subset of x. So with this new more requirement, I can no longer take I to be this itself. Why? Because if this is my I, then you know that the closure is the closed interval 1, 2, which of course is not contained in this. So with this new slightly modified definition, I can take a closed interval, not this one, but something that lies inside this. And then I do not have this problem. I can no longer take this I. Okay, so we are going to go with this slightly changed definition. All right. Now, let's see an example. Let us calculate some alpha lengths. Consider this alpha. What is alpha of x? It is x square, the square function. Then, what will be alpha of the closed interval 2, 3, and make sure that our requirement is met. Okay. What is the closure of this closed interval? Since the closed interval is a closed set, so it is its own closure. And in any case, whatever we are going to consider here, because the domain of alpha is now the largest set that we can possibly consider, so everything is going to be lying inside this. The closure of any subset of R is after all inside R, so no problem. So by definition, this is alpha of 3 minus alpha of 2. So alpha of 3 is 3 square, alpha of 2 is 2 square, 5. However, you can clearly see that the ordinary length is 3 minus 2 equal to 1. So the alpha length is something quite different. Also, you may guess that the general nature of alpha will ultimately make some strange things happen. For example, if you go for the alpha length of this interval minus 3 comma minus 2, well, I think, just to show that all types of intervals can be considered, the author has chosen open interval. So by definition, alpha of the right endpoint minus alpha of the left endpoint, but the function is squaring. So 4 minus 9, this is equal to minus 5. This looks very strange. Length is negative, but it's not ordinary length, it's alpha length. So you can expect some such strange things to happen. And of course, we also have these things. Just by definition, alpha of this degenerate interval is 0, and alpha of the empty set, of course, is also 0 by this part of the definition. So alpha length can be negative if we do not impose any further restriction on the function alpha, on the type of the function alpha. Now, after this, there is a little notational thing, and this may remind you of definite integration. Sometimes, definite integration from school calculus, we write alpha followed by a vertical bar AB, or alpha of x x equal to a, x equal to b, instead of the alpha length of I. I said this reminds you of definite integration because if you are integrating something, what do you do in school? First you find the antiderivative, say something like this. Say you want to calculate this. You know that the derivative of minus cos x is what? Derivative of cos x is already minus sin x, but because we have a minus sign, so you get sin x. So minus cos x is one antiderivative of sin x. So you write minus cos x, and then what you do, either you do something like this or you do like this, and then you know what to do. Because what do? You evaluate this function at 2 minus, you evaluate this function at 1. So is that not alpha length, where in place of alpha you have the function minus cos x? That is why sometimes instead of writing alpha length, we write like this. Okay, now let us see the next example. Now we are going to consider a very special function alpha. This one is also from R to R, and it's nothing but the identity function. Then for a degenerate interval I, of course alpha of I is going to be 0 by definition if I is a non-degenerate bounded interval. With left end A and right end B. That means it's of any of those 4 types, but it's non-degenerate, so A is less than B. Then alpha of I will be what? By definition this is alpha of B minus alpha of A. However, because alpha is the identity function, this is B minus A. So that's the ordinary length of I. Here also, in this case, 0 is also the ordinary length of I. So you see that the ordinary length, or simply length, of a bounded interval is actually a special case of the alpha length, where alpha is the identity function. And that is why the notion of alpha lengths is an extension of the notion of ordinary length. Now we recall a result that we proved when discussing ordinary lengths. It is that if you have a bounded interval I and you have a partition P of I, then if you take the sum of the ordinary lengths of the subintervals in that partition and add them up, you get the ordinary length of I. The similar result is also true for alpha length, and this is called additivity of alpha length. In this case, it's the additivity of ordinary length. So let's see the result. The result, of course, is just that one with length replaced by alpha length. Let I be a bounded interval such that I closure is a subset of X and X is a subset of R. Let alpha from X to R be a function. Okay. So this is our usual setup so that we can talk about alpha length of I. Let P be a partition of I. Then the alpha length of I is equal to the sum of the alpha lengths of the j's which are in the partition. And the similar result we saw earlier, which involves ordinary length, is theorem 11.1.13. Now, how can you prove this one? You don't have to do almost anything. You go back to the proof of theorem 11.1.13. Let me write it down. Theorem 11.1.13. You go back to the proof of this theorem, and there, wherever you have ordinary length, you replace that with alpha length. That will be the proof of this. Exactly same proof, only lengths are replaced by alpha length. That's it. Now, one can go on doing the other further things that we did with ordinary length after proving this theorem there in the theory of Riemann integration, and the exact similar things we are now going to do with alpha length. But at some stage we are going to impose an additional restriction on alpha. We will no longer consider alpha to be any function but a monotonically increasing function. And then that will give us a theory of integration which is parallel to Riemann integrals but is more powerful. Okay, so we will see what that theory is in the next analysis video, next Sunday, and how it gives us more things about Riemann integrals themselves. So I am ending this video here itself. Tomorrow we also have an upload, and that's going to be on trigonometry from class 11. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.